So to continue our discussion in Chapter 5, Stresses in Beams, we have the economic sections. So on this part, makikita natin dito or masasolve natin dito yung mga adequate sizes or economical sizes na need for our beam. So the portions of a beam located near the neutral surface are under stress compared with at the bottom or in the top. So we have here a rectangular cross-section ng beam. So as I have discussed last time, sa neutral axis, the stress is equal to 0. And the statement says that the portions of a beam located near the neutral surface are under stress compared with at the top or the bottom. So when drawing natin yan, so this is the compression side. Ito yung stress at the outermost fiber. And dito naman sa tension side, ito yung stress at the outermost fiber. So, dito yung ating neutral axis, di ba? Yan. On which yung stress dito is equal to 0. So, habang papalapit siya sa neutral axis, papaliit ng papaliit yung stress na na-experience ng ating beam. Therefore, beams with certain cross-sectional shape, including a rectangle and circle, utilize the material inefficiency because much of the cross-section contributes little in resisting the bending moment. So, sa pagpili ng structural section, gagamitin natin as a beam, we note that the resisting moment, so let's say the resisting moment is equal to the stress multiplied by the moment of inertia all over the distance from the neutral axis to the outermost fiber, or familiar kayo, this is Mach all over I. Or pwede rin natin express na stress multiplied by the section modulus. So, the resisting moment must be equal to or greater than the applied bending moment, or it can be expressed as the section modulus must be greater than or equal to the ratio of the resisting moment all over the stress. So, ito yan. So, if the beam is very slender, it may fail by lateral buckling before the working stress is reached. So, for example, meron tayong ditong a W-shaped beam. So, the compression flange is free to displace laterally and rotate. So, itong compression niya, so ito yung flange niya, di ba? And this is the compression flange, and this is the web. So, the compression flange is free to rotate or magkakaroon ng displacement. So, either magkakaroon siya ng buckling or magro-rotate siya. So, imagine nyo na lang magro-rotate itong compression flange niya before the working stress is being reached. So, hindi pa niya na-reach yung working stress niya or yung maximum working stress niya, nagkakaroon na ng deformation. So, I-beams are particularly vulnerable to lateral buckling because of their low torsional rigidity and small moment of inertia about the axis parallel to the web. So, we have procedures for selecting standard shapes. So, first is by determining the maximum bending moment by drawing the bending moment diagram. So, i-drawing natin yung moment diagram by considering only the applied load. So, maneneglect muna yung weight of the beam. So, kung ano yung nai-apply na load sa ating beam, yun muna yung unang mako-consider. So, next is to determine the minimum allowable section modulus. So, kung nakuha na natin yung maximum moment, isosolve natin yung section modulus by having section modulus is equal to the moment divided by the stress. Next is to choose the lightest shape from the list of structural shapes. So, kung nasolve na natin yung section modulus, kukunin natin yung list of sections na may pinakamalapit na value with our allowable section modulus, as well as the lightest shape. So, hindi lang yung pinakamalapit, i-consider din natin yung pinakamagaan sa kanila. So, later on, I will show you on how we'll do it. So, next one is to calculate the maximum bending stress in the selected beam caused by the prescribed loading plus the weight of the beam. If the maximum stress is lesser than or equal to the working stress, the selection is finished. Otherwise, the second lightest shape with section modulus is greater than or equal to the minimum section modulus must be considered, and the maximum bending stress must be recalculated. So, isasama na natin yung weight of the beam in calculating the maximum bending stress. Hindi na lang yung applied load, isasama na natin dito yung bending stress caused by the weight of the beam itself. So, if the maximum stress is greater than or equal to the working stress, pasado na yung section natin. But if not, itratry natin or i-resolve natin yung ibang sections na kasama sa ating list.
What is the lightest W-shaped beam that will support the load shown without exceeding a flexural stress of 120 megapascal? Determine the actual maximum stress in the beam. Assume that the beam is properly braced against lateral deflection. So, meron tayong beam dito and it is being loaded by a 45 kilonewton. So, itong 45 kilonewton na to is the live load na kinikerry ng beam. So, the first step is to determine the maximum moment na nag-a-act dito alone when using 45 kilonewton only. So, by drawing the shear and moment diagram, so we have here 15 kilonewton and then 15 kilonewton. 15 minus 45 is negative 30 and then 30. So, this is the shear diagram. So, the maximum moment is equal to 15 kilonewton multiplied by 4. So, it is equal to 60 kilonewton dot meter. And then, we know that the section modulus is equal to the moment all over the flexural stress. So, moment natin is equal to 60 times 10 raised to 6 newton dot millimeter all over the flexural stress of 120 megapascal. Therefore, the section modulus is equal to it is equal to 500 times 10 raised to 3 cubic millimeter. So, next step is to open your copy for the properties of the steel sections. So, titignan natin yung section na may pinakamalapit na value ng section modulus of 500 times 10 raised to 3 cubic millimeter as well as the lightest one.
So, we have here a table or the properties of wide flange sections in SI units. So, we have here W shapes, S shapes. We also have here equal angles and unequal angles. So, dito makikita nyo yung mga different sizes ng ating W shapes and also yung kanilang mass per unit length, their area, depth, width, thickness, and also the section modulus, the moment of inertia, and then the radius of gyration, etc. So, for our example, the section modulus is equal to 500 times 10 raised to 3 cubic millimeter. So, ito yung kanyang section modulus. So, the first step is to find yung pinakamalapit na value ng 500 times 10 raised to 3 cubic millimeter. So, magsisimula tayo sa baba. So, this is the biggest size. So, punta tayo sa pinaka maliit na size first because we are also considering the lightest shape. So, simulan natin sa baba. So, we have here W100. So, yung section modulus niya must be equal to 500. So, we have here. So, dito sa W100, so wala. Sa W115, wala din. So, sa W200, we have here W200 by 52. So, makikita niya yung section modulus niya is equal to 511. 511. So, lista natin yan. Also, let us proceed to the other size. So, yung 511 is, yung weight niya is around 52 kg per meter. So, let us proceed to the other one. So, sa W250, we have here 531. On which, it is equal to 44.8. So, mas magaan siya compared sa W200 by 52. So, tingin ulit tayo ng iba. Baka may mas magaan pa. So, we have here W310 by 38.7. So, yung section modulus niya is around 547 times 10 raised to 3. And it weighs around 38.7 kg per meter. So, again, mas magaan na naman siya compared sa ating W250 by 44.8. So, hanap ulit tayo. Baka may mas magaan pa. Let us proceed to W360. So, sa W360, we have W360 by 39. So, the section modulus is 578 and it weighs 39 kg per meter. So, medyo mas mabigat na siya ng kaunti sa ating W310 by 38.7.
So, I already have the summary of the W sections na may pinakamalapit sa 500 times 10 raised to 3 cubic millimeter. But we will also consider yung pinakamagaan or the lightest one. So, upon considering all these 4 sections, makikita natin na ang pinakamagaan sa kanila is yung W310 by 38.7. So, by only considering these numerical values, so this one is 52 kg per meter, this one is 44.8, this one is 38.7, and this is 39. So, ang pinakamagaan is yung ating W310 by 38.7. So, let us try to evaluate kung kakayanin ba ng section na to yung loading natin na 45 kN as well as kung idadagdag na natin yung dead load. So, the dead load of this section would be equal to 38.7 kg per meter. So, convert lang natin siya into Newton per meter by multiplying it by 9.81 meter per second squared. So, it is equal to 379.647 Newton per meter, or 0.379 kilonewton per meter. So, kukunin natin yung moment from the dead load. So, kung i-drawing natin yan, ito yung beam. So, yung dead load niya is equal to 0.379 kilonewton per meter. So, this is 6 meters. So, 0.379 times 6 times 3 divided by 6. So, 1.137 kilonewton and 1.137 kilonewton. So, the maximum moment would now be equal to 1/2 of 1.137 multiplied by 3. So, 1.7055 kilonewton dot meter. And then, yung moment from the live load is equal to 60 kilonewton dot meter. And yung ating resisting moment must be greater than or equal to the sum of the moment from the dead load and the live load. Or, the section modulus of the resisting beam must be greater than or equal to the section modulus of dead load plus the live load. On which, the section modulus is equal to yung moment natin. So, 1.7055 times 10 raised to 6 Newton that millimeter all over yung flexural stress of 120 megapascal. So, it is equal to 1.7055 all over 120. So, we have 14.21 times 10 raised to 3 cubic millimeter. And then yung section modulus natin for the live load is equal to, yung na-compute natin kanina, it is equal to 500 times 10 raised to 3 cubic millimeter. And then yung ating section modulus of the beam is equal to 547 times 10 raised to 3 cubic millimeter. So, itetestify na natin ngayon kung tama ba or kung na-meet ba niya itong restriction na to. So, we have 547 times 10 raised to 3. Is it greater than or equal to 500 times 10 raised to 3 plus 14.21 times 10 raised to 3. Tama, na-meet niya yung ating limit. So, we have 414 times 414.21 times 10 raised to 3 cubic millimeter. So, next is to determine the actual maximum stress by having the actual stress is equal to the actual resisting moment all over yung ating section modulus of the beam. So, we have 1.7055 plus 60 times 10 raised to 6 Newton that millimeter all over 547 times 10 raised to 3 cubic millimeter. Therefore, the actual maximum stress would now be equal to 112.81 megapascal. This is the actual maximum stress if we use a W310 by 38.7. So, this would be our answer. So, for example number 2, a 10-meter beam simply supported at the ends carries a uniformly distributed load of 16 kN per meter over its entire length. What is the lightest W-shaped beam that will not exceed a flexural stress of 120 megapascal? And what is the actual maximum stress in the beam selected? So we have a 10-meter beam that is simply supported. So this is 10 meters. So it has a uniformly distributed load of 16 kilonewton per meter. So meron siyang load na 16 kilonewton per meter. So again, the first step is to determine the moment from the live load. So we have here the reaction 1. So we have 16 times 10 multiplied by 5 divided by 2. So we have 80. This is 80 kilonewton and this is 80 kilonewton. So the shear diagram, so kung na-draw nyo yung shear diagram, pwede nyo i-diretso yung pagkuha ng moment. So on the next chapter kasi, we will be discussing yung formula base ng pagkuha ng ating moment without drawing or without illustrating the shear and moment diagram anymore. So, but for now, we will still consider the shear and moment diagram. That is for the next chapter na lang. So, we have here 80. So, this is 80 kilonewton and this is 80 kilonewton. So, the moment would now be equal to 1/2 of 80 multiplied by 5. So it is equal to 200. So it is equal to 200 kilonewton dot meter. So the section modulus na dapat natin i-consider is equal to 200 times 10 raised to 6 divided by the flexural stress of 120 megapascal. So it is equal to 1066 or 1666.67 cubic millimeter. So again, opening your copy for the properties of steel sections.
Section modulus is equal to 1666.67 cubic millimeter. So magkahanap tayo ng section na may malapit sa 1666.67 by starting at the bottom. So muna tayo sa baba. So for W100, wala. 130, wala din. Also at 150, wala din. 200. So 200, so 990 yung pinaka malaki dito. So let us proceed to W250. So sa W250, we have W250 by 149. So yung section modulus niya is equal to 1,840. So yan, take note of this one. So hanap pa tayo ng mas magaan because this section weighs 149 kg per meter. Let us proceed to W310. So sa W310, we have W310 by 117. Yung section modulus niya is around 1,750. And it weighs 117 kg per meter. So hanap pa tayo ng mas magaan. So we have also W360 by 101. So yung section modulus niya is 1690 and it weighs 101 kg per meter. So hanap pa tayo, baka may mas magaan pa. Also we have W410 by 100. So yung section modulus niya is 1920 and it weighs 100 kg per meter. So mas maganda naman siya. So marami pa tayong pagpipilian. So we also have W460 by 89. So yung section modulus niya is 1770 and it weighs 89 kg per meter. Tingnan natin dito sa taas, baka meron pa. So sa W530 by 85, meron din tayo which is 1,820 and yung weight niya is 85 kg per meter. So mali siguro to, so baka 1,900 ito kasi pataas ng pataas yung section modulus niya. Maybe this is 1,900. Next, we also have W610 by 82. So it has section modulus of 1,870 and it weighs 82 kg. And we have also a W690. So masyado nang malayo sa section modulus na hinahanap natin which is 1,666.67 and masyado na ring mabigat compared to our W610 by 82.
So I have here now the summary ng mga na-consider nating may pinakamalapit na value ng section modulus. So we have here 7 sizes of W-shaped section. So ang pinakamagaan sa kanila is the W610 by 82. So again, i-consider natin yung pinakamagaan among them. So we have W610 by 82 with a section modulus of 1,870 times 10 raised to 3 cubic millimeter. So let us try to evaluate kung mag-e-exceed ba siya or hindi sa flexural stress natin of 120 megapascal. Next, we'll determine the dead load or the moment from our dead load. So, yung dead load natin would be equal to 82 kilogram per meter. So, multiply natin ng 9.81. And then, divide natin siya ng 1/1000 para maging kilonewton per meter na lang. So, 82 times 9.81 over 1000. So, we have 0.8044 kilonewton per meter. Next is the dead load. So, gawin na lang natin. On the next chapter na lang yung formula base. So, we have here 0.8044 kilonewton per meter, and this is a 10 meter. So, the reaction is equal to, so this is 4.022 kilonewton. So, sabi ko nga, kung gaman nyo na itong pag-drawing na shear and moment diagram, mandali na lang. So, we have here. Therefore, the moment from the dead load would be equal to, so it is equal to 10.055 kilonewton dot meter. So, the resisting moment is equal to 10.055 plus yung 200 natin kanina. So, it is equal to 210.055 kilonewton dot meter. And then, yung ating SL is equal to 166.67. And yung ating section modulus is equal to 10.055 times 10 raised to 6 Newton dot millimeter all over yung flexural stress natin of 120 megapascal. 10.055 so this is equal to 83.79 times 10 raised to 3 cubic millimeter. Therefore, the section modulus of the resisting beam is now equal to 1870 times 10 raised to 3 cubic millimeter. So, titignan na natin kung masasatisfy ba na yung ating limit SD plus SL. So, 1870 times 10 raised to 3. SD natin is 83.79 plus 166.67. So, 166.67 plus 83.79. So, yan. So, na-satisfy niya yung ating limit. So, 170.46. Therefore, we will use W610 by 82. So, since nasatisfy niya yung ating condition, we will use W610 by 80. So, next is to determine the actual maximum stress in the beam by dividing the resisting moment and the section modulus. So, our resisting moment is equal to 210.055 kilonewton dot meter and our section modulus is equal to 1870. So, the actual maximum stress now would now be equal to 112.33 megapascal if we use W610 by 80.
Next is we have our floor framing. So basically, ang pinaka-common na gamit ng ating beam is to provide support for the floors and of course to provide frameworks for the building. So we have here a typical section for our floor framing. So makikita natin we have here a subfloor, And yung subfloor natin is being supported by our floor joist. So, ito yung ating floor joist. So, yung floor joist natin is spaced or equally spaced with a distance A. So, yung floor joist natin, pinubuhat niya yung half of the load ng left floor and the right part. So, yung floor joist natin, pinubuhat niya yung load A over 2 and yung load at the other side which is A over 2. So, binubuhat niya yung half of the load from the left floor and also at the right part of the floor. So, yung ating floor joist, kung i-drawing natin yung load diagram niya, it will look like this one. So, this is the floor joist. So, i-convert natin yung floor load into a uniformly distributed load. So, convert natin siya in a uniformly distributed load. So, magkakaroon na ng reaction 1 and reaction 2. So, yung R1 and R2 natin. So, dito yung R1 and dito yung ating R2. So, let's say, dito naman, we have here, so doing the same step, we have here S1 and here is the S2. And let's say this is T1 at dito yung part na to is the T2. So, yung floor joist natin is kinikerry naman ng ating girder. So, yung girder, kung drawing naman natin yung ating floor diagram or the load diagram, mapapasa na yung load na T1, R1, and S1 So, yung load na T1, R1, and S1 is napapasa sa ating girder kaya nagkakaroon na ng reaction from our girder. So, let's say this is RG1 and this is, or let's say this is R1G and this is R2G, on which yung ating load from the girder is binubuhat naman ng ating column. So, yung value ng R1G natin and R2G natin is being passed to the column. So, kung ano man yung value ng R1G mo dito and R2G mo dito, pinapasa mo na siya sa column up to the foundation. So, again, the weight of the floor is being carried by the floor joist. So, i-convert lang natin yung floor load into a uniformly distributed load. So, makakuha na tayo ng end reactions from our joist. And then, yung joist natin is being carried by the girder. So, kung ano man yung loading ng floor joist mo, is pinapasa mo na siya sa girder. And then, kung ano man yung loading ng ating girder, it is being passed on to the column. Kaya, dito natin makikita or dito natin masosolve the size of the columns as well as the size of the foundations later on.
For example number 1, determine the loading diagrams for beams B1, G1, B2, and G2 for the building whose partial floor plan is shown. So we have here the floor framing plan of a building. We have different kinds of beam. We have B1, this is B2. We also have G1, G2. So each floor has a loading of 5 kN per square meter on this part, and the rest has a loading of 10 kN per square meter. So kindly take note that each beam carries half of the loading of each floor. So for example, itong beam 1 natin, binubuhat niya yung loading ng half ng floor na to. And also, yung half ng floor nito. Yan. So, beam 1 carries half the load of each floor. So, drawing the loading diagram of beam 1. So, we have, so yung beam 1 natin, yung length niya is 6 minus 2. So, we have 4 meters. And then, we have reaction 1 and reaction 2. So, yung support niya is on this part and on this part. So, kung drawing natin yung loading diagram ng floor na to, so we have 5 kilonewton per square meter multiplied by half. So, 1 meter. So, meron tayong, so this is 5 kilonewton per meter from the left side or from the left floor, and then 5 kilonewton per square meter multiplied by 1 naman from the right floor. So, yan. So, this is 5 kilonewton per meter. So, drawing natin. So, simplify natin yung drawing. So, the reaction at each side would now be equal to 10 multiplied by 4 multiplied by 2 divided by 4. So, we have here 20 kilonewton. And this is also 20 kilonewton. So, this is 20 kilonewton, 20 kilonewton. And then, yung uniformly distributed load of 10 kilonewton per meter. So, ito na yung ating loading diagram for beam 1. So, next is our G1. So, yung G1 natin, nakapatong siya sa ating B2. And then, nakapatong naman yung B1 natin sa G1. So, kung i-drawing natin yung loading diagram, so this is our G1 and it has a length of 6 meters. So, 6 meters. So, nakapatong yung ating G1 sa ating B2. So, we have here reaction 1 and reaction 2. Nakapatong naman yung ating beam 1 or yung B1 natin sa G1. Therefore, yung end reaction, so, di ba yung end reaction ng ating B1 is 20 kilonewton? So, ililipat lang natin siya sa ating G1. So, we have here 20 kilonewton. Also, here we have 20 kilonewton. Okay, so, ito yun. So, for example, ito yung R1 and this is R2. So, yung R2 natin, ililipat lang natin sa G1. So, we have here 20 kilonewton and also here, we have 20 kilonewton. Therefore, yung reaction 1 natin would now be equal also to 20 kilonewton and this is also 20 kilonewton. So, ito na yung ating loading diagram for our G1. Next is yung ating B2. So, yung B2 natin has a span of 6 meters. So, 6 meters. And then, yung ating B2 is nakapatong sa ating columns. By the way, these are the columns. Itong mga to. So, we have here reaction 1 and reaction 2. So, yung kine-carry ng ating B2 is the half of the loading from the right floor and also the half the loading of from the left floor. In addition, meron pang loading from our G1. So, nasabi ko kanina yung ating G1 is nakapatong sa ating B2. Kaya, we have 3 loadings here. 1 is loading from the right floor, half of the right floor. So, is naka-span siya ng 6 meters. So, the entire length ng ating G1 is merong 10 kilonewton per square meter multiplied by 1 meter. Kasi yung half lang yung i-consider natin, right? So, we have 10 kilonewton per meter. Next one is the loading from the left floor, which is yung ating half. Yung half ng loading from the left floor. So, it is 5 kilonewton per square meter multiplied by 1 meter. So, meron tayong 5 kilonewton per meter and it is only acting 4 meters from the left support. So, let's say this is the left support and this is the right support. So, rotate lang natin siya. So, it is acting 4 meters from the left support. So, 4 meters lang. So, let's say this is 4 meters and then the rest is 2 meters. So, merong 5 kilonewton per meter. So, ito yung portion na to. And then, yung end reaction ng ating G1 which is 20 kilonewton and it is acting 4 meters from the left support also. So, yung ating end reaction ng G1 is 20 kilonewton. So, meron pang nakapatong ulit na 20 kilonewton. So, we will now determine the reaction from 1 and 2. So, taking the summation of moment at R1 is equal to 0. So, we have 15 kilonewton per meter. multiplied by 4 meters, moment arm is 2 meters, plus 10 kilonewton per meter, length is 2 meters, moment arm is, so lagay ko na lang dito, 1 meter plus 4 meters, plus yung 20 kilonewton natin, moment arm is 4 meters, minus reaction of 2, 6 meters is equal to 0. Therefore, the reaction 2 is equal to, we have 15 times 4 multiplied by 2 plus therefore R2 is equal to R2 is equal to 50 kilonewton. So, yung R2 natin is equal to 50 kilonewton. Therefore, R1 is equal to, so by taking the summation of forces vertical, so it's equal to 14 times 4 plus 20 plus 10 of 2 minus 50. So, our R1 is equal to 50 kilonewton. So, this is also equal to 50 kilonewton. So, ito na yung ating diagram or load diagram for B2. So, ito na yun. So, isolve muna natin yung reaction or yung load diagram ng ating B3. So, for B3, so yung span ng ating B3 is 6 meters. So, yung loading niya from the left floor is equal to 10 kilonewton per square meter multiplied by 1. So, we have 10 kilonewton per meter. And also, from the right side, half of the loading, parehas lang. So, it is equal to 10 kilonewton per meter. Therefore, the end reaction would now be equal to, so we have 20 kilonewton per meter multiplied by 6 multiplied by 3 divided by, so we have here 60 kilonewton and 60 kilonewton. Therefore, yung end reaction na nag-a-act sa ating G2 is equal to 60 kilonewton. So, ito yung 60 kilonewton, may 60 kilonewton dito. So, our G2, so for G2 now, its length is equal to 6 meters. So, 6 meters. So, this is the reaction 1 and reaction 2. So, yung end reaction from B3 is equal to 60 kilonewton. So, we have 60 kilonewton, 2 meters from the left support, and also another 60 kilonewton, 4 meters from the end support. So, this is 2 meters. Therefore, the end reaction now is equal to, so summation of forces vertical. So, this reaction is equal to 60 kilonewton. And then also yung reaction here is also 60 kilonewton. Therefore, this is now the load diagram for our G2. So, for example number 2, floor joists 50 millimeters wide by 200 millimeters high, simply supported on a 4 meter span, carry a floor load that is loaded by 5 kilonewton per square meter. Compute the center line spacing between joists to develop a bending stress of 8 megapascal. And what safe floor load could be carried on a center line spacing of 0.4 meters? So, meron daw tayong floor joist that is 50 millimeters in width and 200 millimeter in height, and it is simply supported with a span of 4 meters. So, simply supported siya, and it carries a loading of 5 kilonewton per square meter. So, first is to convert this 5 kilonewton per square meter into a uniformly distributed load. But the problem is requiring for the spacing between joists. So, kung i-drawing natin yung floor framing niya, so ito yung mga joists natin. That is 200 mm in height and 50 mm in width. So, ito yung mga floor joists natin. And it carries a floor load. So, let's say this is the floor. And it carries a floor load of 5 kilonewton per square meter. So, ito yung mga 5 kilonewton per square meter. So, ito yung mga joists natin. So, these are the joists. So, nire-require ng problem or hinahanap ng problem yung mga spacing ng ating joist to develop a bending stress of 8 megapascal. So, let's say this is A. Yung spacing ng ating joists. So, this is A. So, as I have said earlier, ang kinikerry ng isang joist is the loading or the half the loading of the left floor and also with the right floor. So, ito yung kinikerry ng ating joist. So, let's say, yung kinikerry at this part is 5 kN per square meter multiplied by A over 2. So, this is now A over 2 and this is A over 2. So, 5 kN per square meter multiplied by A over 2. So, meron tayong 5 A over 2 kN per square and kilonewton per meter. And from the right side, meron naman tayong parehas lang, meron ding 5 multiplied by A over 2 kilonewton per meter. Therefore, yung load diagram natin for that joist would be equal to, so 5A over 2 plus 5A over 2 is equal to 5A kilonewton per meter. So, meron tayong reaction 1 and reaction 2. So, yung reaction 1 natin at this part, so this is 4 meters. So, yung R1 natin is equal to 5 multiplied by 4. It is equal to 10A kilonewton. And this is also 10A kilonewton. So, pupunin natin yung moment. So, yung shear muna natin is, this is 10A. This is also 10A. Yan. Ito na yung ating shear diagram. Therefore, the moment would now be equal to 1/2 of 10A multiplied by 2 meters. So, the moment is equal to 10A kilonewton dot meter. And we know that the bending stress is equal to our Mach all over I, diba? So, yung bending stress natin is equal to 8 megapascal. Yung moment is equal to 10A times 10 raised to 6 Newton dot millimeter. And then, yung C natin is, so dito yung neutral axis. So, yung C is equal to 100 millimeters. This is equal to 100 millimeters. So, 100 millimeters. And then, yung moment of inertia ng ating joist, which is rectangle. So, 1 all over 12 BH cubed. So, B is 50. Height is 200 raised to 3. Therefore, A is equal to 8 times. Therefore, A is now equal to, so we have now 0.267. So we have Newton per square millimeter, millimeter cube, Newton per millimeter, then Newton per millimeter squared. So we have 0.267 millimeter. So times lang natin ng 1,000. So it is equal to 267 millimeter. So, yung spacing ng ating joist would now be equal to 267 millimeter. So, ito na yung hinahanap ng ating problem. So, the center line spacing between joists is equal to 267 millimeter to develop a bending stress of 8 megapascal.
So, next is on how we will determine the bending stresses in unsymmetrical beams. So, yung mga examples natin on the first part are so far mostly symmetrical or almost symmetrical lahat with respect to the neutral axis. So, yung mga shape na yan are desirable for materials that are equally strong in both tension and in compression. So, paano naman yung mga sections that are weak in tension but strong in compression? Like for example, yung mga cast iron natin, a shape or mga W shape. So, it is desirable to use beams that are unsymmetrical with respect to the neutral axis. So, with such a cross-section, the strong fibers can be located at a greater distance from the neutral axis than the weaker fibers. So, the ideal treatment for these materials is to locate the centroidal or the neutral axis in such a position that the ratio of the distances from it to the fibers in tension and in compression is exactly the same as the ratio of the allowable stresses in tension and in compression. So we have here a procedure in determining bending stresses in unsymmetrical beams. First is to identify the largest positive and negative bending moments by drawing the bending moment diagram. Next is to locate the neutral axis or the centroidal axis and record the distances from the neutral axis to the top and bottom of the cross section. Third one is to compute the moment of inertia of the cross section, lalo na kung hindi given yung moment of inertia from the properties. So calculate the bending stress at the top and bottom of the cross section where the largest positive bending moment occurs from this formula. So for example, we have here a I-beam or our W shape. We have here our wide flange. So ito yung ating neutral axis, for example. So ito yung C top and this is the C bottom. So this is our formula in which our stress is equal to negative moment multiplied by y all over I. So kung i-consider natin the top of the cross section, our stress would now be equal to negative moment multiplied by C top all over I. Or in other words, upward or the distance upward to the neutral axis is positive and then yung pababa is considered as the negative. So kung compute natin yung stress is equal to negative moment all over y or negative moment times y all over I. So multiply by natin with positive value ng y. So makakuha tayo ng negative stress. So kung sa bottom part naman of the cross section where y is equal to negative c bottom, so pababa tayo, so we will consider the negative value ng ating y. So makakuha tayo ng negative multiplied by negative, so makakuha tayo ng positive stress. So change this one, this is bottom, stress in bottom. So repeat the calculations for the cross section that carries the largest negative bending moment, and then inspect the four stresses thus computed to determine the largest tensile for positive and compressive bending stresses in beam. So kung naaalala nyo, our tension is positive value and the compression would be in negative value or the negative bending stress in our beam.
So for example number 1, a cast iron beam carries a uniformly distributed load on a simple span. Compute the flange width B if the inverted T-section so that the allowable stress per tension is equal to 30 megapascal and the compressive stress is equal to 90 megapascal. Reach their limit simultaneously. So we have here inverted T-section or inverted beam that has an allowable stress of 30 megapascal for tension and an allowable stress for compression of 90 megapascal. So kukunin natin or hahanapin natin yung uniformly distributed load na kinikerry ng beam. I have discussed before, the neutral axis is experiencing no stress. Thus, yung mga fibers na malapit sa ating neutral axis is under stress. So we have here a diagram for the compressive stress. So this would be yan. So ito yung compressive stress and ito naman yung tensile stress. Kung papansin nyo, as the distance is going near the neutral axis, papaliit naman yung value ng ating compressive stress and also with our tensile stress. So kung nandito na siya sa neutral axis, nawawala na yung stress or nagkakaroon na ng no stress. Thus, itong mga fibers dito malapit sa neutral axis is kinakonsider nating under stress. So, ito yung ating YC or yung distance from the neutral axis to the outermost fiber. And ito naman yung ating distance from the neutral axis to the outermost fiber in tension zone. So, by ratio and proportion, I can say that YC plus YT all over the compressive stress plus the tensile stress is equal to YC all over stress for compression. So we have YC plus YT So, makakancel out ito. Therefore, the distance from the neutral axis to the outermost fiber in tension zone all over the distance from the neutral axis to the outermost fiber for compression zone is equal to the stress or tension all over our compressive stress. In which, yung ating compressive stress is equal to 90 megapascal and this is 30 megapascal. And also, our YT is equal to 140 minus YC. Tama? So, we have, substitute natin to. So, we have 140 minus YC all over YC is equal to 1/3. Therefore, YC is equal to, so we have in YC is equal to 105 millimeter and our YT is equal to 35 millimeters. Now, considering that the T-section consists of two rectangles. So, this is rectangle 1 and this is rectangle 2. Since the neutral axis coincides with our centroidal axis, we will take a moment of areas with respect to the x-axis. So, ito yung magiging x-axis natin. So, we will take summation of moment with respect to this axis through the base of the flange. Thus, we have an equation of summation of AY. So, yung area natin is 120 millimeters multiplied by 20 plus area natin for B or for the second rectangle. So, we have 20 millimeters multiplied by B. And then, the distance from the axis to the neutral axis. So, we have YT, in which our YT is equal to 35 millimeters. Is equal to summation of moment or summation of area multiplied by the distance to the neutral axis. So, we have 120 multiplied by 20 millimeters. And then, yung centroid nito is 20. So 60. So, 60 plus 20. So, we have 60 plus 20 plus itong rectangle dito sa baba. So, we have 20 multiplied by B. And then, 20 all over 2. Therefore, the B is equal to 120 times 20 plus 20. Right? Therefore, the flange with B would now be equal to 216 millimeters. So this would be our final answer. For example number 2, compute the maximum tensile and compressive stresses developed in the beam that is loaded and has the cross-sectional properties as shown. So the first step is to draw for the maximum or to draw the moment diagram. So we have summation of moment R2 is equal to 0. So we have R1 multiplied by 10 minus 400 of 10 multiplied by 5 plus 1000 multiplied by 4 is equal to 0. Therefore, the reaction 1 is equal to R1 is equal to 1,600 pounds. And then R2 is equal to, by taking the summation of forces vertical, so R2 plus R1 minus 400 times 10 minus 1000 is equal to 0. Therefore, R2 is equal to, so transpose natin, so it is equal to 3,400 pounds. So R1 is 1,600, R2 is equal to 3,400. So for the shear diagram is 1,600. So we have 1,600 minus 400 of 10. So we have here 2,400. Negative 2,400 plus 3,400. So we have 1,000. This is 1,000. So this is our shear diagram. So we will locate the distance of the zero shear para ma-determine natin yung maximum moment. So at this part, so by ratio and proportion, we have 1,600 plus 2,400 all over 10 is equal to 1,600 all over x. So this is x. Therefore, x is equal to so it is equal to 4 meters. So x is equal to 4 meters. So this is 4 meters. Therefore, this is 6 meters. So drawing the moment diagram. So we have here, do we have a moment 0, and then moment here is equal to 1/2 of 4 times 1,600. So 3,200. We have here the maximum moment of 3,200 minus 1/2 of 6 multiplied by 4. So we have 4,000 pounds per, or pounds per feet. And then plus 1,000 of 4. So 0. So ito yung magiging itsura ng ating moment diagram. So it will look like this one. And after this, we will draw the elastic diagram. So ano ba yung elastic diagram? So yung elastic diagram will illustrate kung paano yung bending ng ating beam, kung paano mag-deform yung ating beam. So yung elastic curve natin, elastic curve pala, hindi elastic diagram. So yung elastic curve natin, if the moment is increasing, the curve will be concave upward. But if the moment is decreasing, the elastic curve will concave downward. So drawing this one, so ito. So makikita natin na mayroong increase of moment. So pag may increase, it will concave upward. So let us say that this line is yung original beam natin, original beam. So ito yung original straight illustration ng beam natin. So concave upward. So for this part, magkakaroon ng elastic curve that will concave upward. And then at this part, nag-i-increase siya. So merong concave downward. So magkakaroon ng concave downward. Ayan. So parang ganito yung illustration ng ating deflection ng ating beam. Ayan. On which, kung makikita natin, nag-curve yung ating elastic or nag-curve yung ating beam at this part kung saan dito sa bottom part na to is nakaka-experience ng tension. Why tension? So, let's see this part. Ito yung beam natin. Yan. So, this part nagkaroon ng curvature in which nakaka-experience ng beam natin dito ng tension kasi nag-increase or nag-lengthen yung kanyang size or yung fiber, and then at this part nag-compress kaya nagkakaroon ng compression. And at this part naman, makikita nyo, so lagay ko dito, parang ganyan yung beam natin. So dito na nagkakaroon ng tension, there is increase in length, and at this part nagkaroon ng compression. So dito na yung compression side at this part. So makikita nyo yung difference nya. So at this part, consider nating moment dito is 4,000 pounds foot, and at this part, i-consider nating moment is 3,200 pounds foot. So yung ating compression, yung ating stress is equal to Mach all over I or My all over I. So that is for compression and also for tension. So YC, this is YT, and this is I. So yung moment na i-consider muna natin, this part is a 3,200 pounds foot. So 300,200 pounds foot multiplied by yung ating distance from the neutral axis to the compression side, which is 2 inches, or convert natin into feet. So 2 divided by 12 all over yung I natin. So yung I natin is given by 60 inches raised to 4. So we have 60 inches raised to 4 multiplied by 1 or over 12 raised to 4. Therefore, the compressive stress would now be equal to 184,320 pounds per square foot. But I want to convert it into PSI na lang para mas compatible and mas madali. So, times 1 all over 12 squared. We have here 1,280 pounds per inch square or PSI. And then so take note na lang ito yung part na to. And then for our tensile stress, 3,200 multiplied lang natin siya into, so yung ating YT. So itong 3,200 pounds foot na lang isi-convert natin to pounds per inches squared by multiplying it by 12. And then yung ating distance is 5 inches. So 5 inches all over. Yung ating moment of inertia is 60 inches raised to 4. Therefore, the tensile stress now be equal to, so yan, direct na siya into PSI. So it is equal to 3,200 PSI. So this one is, if we consider 3,200 pounds foot. And for the other side naman, i-consider naman natin yung moment the negative moment of 4,000 pounds foot. So we have here my E all over I. So i-consider natin is yung 4,000. So itong figure na to. So we have 4,000 pounds multiplied by 12. And so multiply natin siya into 5 inches. So bakit 5 inches? So 'di ba, compression side. Dito na yung magiging distance natin from the neutral axis to the compression side, kasi makikita natin na compression niya is nasa baba na. So 5 inches yung i-consider nating distance. 5 inches all over 60 inches raised to 4. Therefore, the compressive stress would now be equal to 4,000 times 12 times 5 all over 60. So we have 4,000 psi. And then for the tension side, we have MYT all over I. So we have 4,000 pounds foot multiplied by 12. Ang i-consider na natin distance, tension side, so tataas na, so 2 inches. So tension side, 2 inches. All over 60 inches raised to 4. Therefore, the tensile stress would now be equal to 1,600 psi. So, ayan. I-compare lang natin yung mga nakuha natin. So, and then i-consider natin yung larger. So, for the compression, for the compressive stress, so 1,280 psi versus 4,000 psi. Therefore, consider natin is 4,000 psi. And then, for the tensile stress, 3,200 psi versus 1,600 psi. Therefore, consider natin yung 3,200 psi. Therefore, these are now the maximum tensile and compressive stress that will be developed in the beam that is loaded as shown. So, this is the final answer. For example number 3, the overhanging beam is made of cast iron for which the allowable stresses are 40 megapascal for the tension and 100 megapascal for compression. If the properties of the cross-section are as shown, determine the maximum uniformly distributed load that can be supported. So, hahanapin natin yung uniformly distributed load dito sa ating beam if our cross-section will look like this one. So, we have the allowable stress of 40 megapascal for tension and 100 megapascal for compression. So, our first step again is to draw the shear and moment diagram para makita natin yung itsura ng elastic curve natin. So, we have here, taking the summation of moment at R2 is equal to 0. Therefore, we have R1 multiplied with 3 meters minus yung W multiplied by 4.2. Moment arm is 2.1 plus W 1.2, moment arm is 0.6, is equal to 0. So we have 3R1. So transpose lang natin. We have 4.2 plus 2.1. No, 4.2 times 2.1 plus 1.2 of 0.6. So, transpose natin. So, we have 8.1 of W. Therefore, the reaction 1 is equal to 8.1 divided by 3. So, we have 2.7 of W. Also, our R2 now are taking the summation of forces vertical. So, we have 2.7 W also. So, yan. So, drawing natin yung shear diagram. So, we have here 0. And then, yung R1 so we have here 1.2. So, negative 1.2 of W. Negative 1.2 plus 2.7. So, we have 1.5. This is 1.5 W. Minus 3. So, we have here negative 1.5 W plus yung R2 natin of 2.7. So we have 1.2, and then we have here minus 1.2 times 1, so we have 0. So ito na yung ating shear diagram. So by taking ratio and proportion, or by just looking at this figure, this would be equal to 1.5 meters. So 1.5 yan, 1.5 din yan. So this would also be 1.5 meters by ratio and proportion, or by looking at the figure alone. So yan, so makikita, mag-drawing na natin yung moment diagram. So for the moment diagram naman, we 0 dito, and then you have negative 1/2 of 1.2 multiplied by 1.2. So meron tayong negative 0.72 of W plus 1/2 of 1.5 times 1.5. So we have 0. Yan. We have 0.405 W as the maximum moment on this part, and then minus 1/2 of 1.5 multiplied by 1.5. So we have here negative 0.72 plus 1/2 of 1.2 multiplied by 1.2. So we have here 0. So ito, concave downward. Yan. So ito yung magiging itsura ng ating moment diagram. For the moment diagram, makukuha na natin dito yung elastic curve. So yung elastic curve, let's say this is the original beam. Yan. So since this is decreasing, yung kanina sinabi ko kanina that if the moment is decreasing, concave downward, and if the moment is increasing, concave upward. So this is decreasing, and nandito yung support, so most probably ganito ang magiging elastic curve. Ayan. So we have 3 points here. Is point 1, point 2, and point 3. So for point 1, so dito sa point 1 and point 3, so yung point 1 and 3 natin, so let's say dito. So yung point 1 and point 3 natin, yan, lakayan lang natin yung figure. So ito na yung beam. So ito na yung tension side, and this would be the compressive side or the compression zone. And for our point 2, ayan, so ito naman yung beam. So ito na yung compression zone, and this would be the tension zone. So take note that the negative sign here denotes or indicates that the upper fibers are in tension zone. So negative to, kaya tama, yung tension zone natin is in the upper fiber. Therefore, we have here, diba yung moment natin would be equal to the compression, or the allowable stress multiplied by the moment of inertia all over the distance, yt. So we have here 0.72. So pwede nyong i-neglect yung negative sign, because the negative sign indicates only that the fiber in upper side is in tension. So 0.72 of W is equal to the compression cut is equal to the allowable stress in tension. So we have 40 megapascal multiplied by the moment of inertia, which is 50 times 10 raised to 6, and then the distance to the tension zone, which is 80 millimeters. Therefore W is equal to 0.4 So it is equal to 34.72 kilonewton per meter. Also, for the compression naman, have MC. So 0.72 of W is equal to 100 megapascal multiplied by 50 times 10 raised to 6 all over yung distance, which is 180 millimeter. Therefore, W is equal to, so we have 38.58 kilonewton per meter. Therefore, ang i-consider natin at this part is the 34.7. So, evidently, yung tension will govern since the safe resisting moment is the lower value. So, i-consider natin yung lower value, which is 34.72 kilonewton per meter. Pero hindi pa natatapos dyan because we will consider also yung point 2, on which yung moment is equal to 0.405 W. So, take note of this 34.72 and we will compare it later on. So, let us proceed dito naman sa point 2 natin. So, sa point 2, same then, we have the moment. The moment na natin is 0.405 of W is equal to yung tension natin is 40 megapascal. So, 40 newton per square millimeter. And then, 50 times 10 raised to 6. Yung ating moment of inertia. And then, so makikita nyo dito, point 2. So, yung tension zone na is nasa baba. So, i-consider natin is 180 millimeters. So, we have 180 millimeters. Therefore, the uniformly distributed load is equal to 0.405 times 180. So, 40 times 50. So, over 180 times 1.405. So, this is equal to 27.44 kilonewton per meter. And also, for the compression, so we have 0.405. Compression is 100 megapascal. And then 50 times 10 raised to 6 millimeter raised to 4 all over. Yung distance from the compression fiber to the neutral axis is 80 millimeters. So 80 millimeters. Therefore, the uniform distributed load is equal to, so this is 80 and this is 100. So it is equal to 154, 100, so 0.405 times 80, 100 times 50 times 50. So we have 154.32 kilonewton per meter. So again, ang i-consider natin is the lowest value or the lower value. So ito i-consider natin. So 27.4. Okay. So comparing the two, we have 34.72 kilonewton per meter and 27.44 kilonewton per meter. Evidently, we will consider 27.44 kilonewton per meter as the safest value or the maximum safe load na kayang buhatin ng ating beam. Therefore, we have 27.44 kilonewton per meter as the maximum safest load. So this would be our final answer.